Let's consider a situation where we can measure the common ion effect. And by that, I mean measure the pH of a solution where we mix both HA and A- together in starting concentrations into the same container. So we know that we would usually have our equilibrium set up, describing our weak acid. And we could make an ice table, and then our problem would tell us some starting concentrations that we could use, or a way to find some starting concentrations. I'll make some up right now for an example. There we go, 0.15, and no starting concentration for H+. Now we know, depending on the K value, that this equilibrium will not shift very largely to the right because this A- common ion will resist that change in pH. But we can still write in our ice table -x, +x, and +x. However, we know that this x is going to be very small. So we can go ahead and mentally use our 5% approximation. Now we could go ahead and write our K expression and fill in our algebra, find our K value in a table, and solve for x, and then put that x into the negative log. And that would be really fun and totally possible. But there's a better way to go. In fact, if you take our original Ka expression and do a little of math magic to it, we can come up with a much more useful way of solving this problem. Starting with our equilibrium constant expression for our acid, we can take the log of both sides. Now, this may not seem like much right now, but we can start to see a few patterns that get to be pretty interesting. For example, I recognize that log of H+ has a little bit something to do with our pH definition. So I'm going to rearrange my logs here using some really cool log rules. If I remember correctly from algebra class when I was a kid, if you have the log of two things that are multiplying each other, that really means the log of x plus the log of y. So what I'm going to do is I'm going to treat these guys like they're y and treat the h like it's x and separate these two things. So in my next step, I look like log of Ka equals log of H+ plus the log of our anion divided by the weak acid. Now that's pretty cool. However, I see that this piece is very, very close to our pH definition, but it's not negative. So what I'm going to do is I'm going to change the places of these two pieces by subtracting them both onto the other side of the equation. That gets me negative log of H+, which matches our pH definition, equals negative log of Ka plus the log of A- over HA. When you simplify this expression to use p's where you see negative log, you come up with something called the Henderson-Hasselbalch equation. It's extremely useful for solving buffer problems. Especially if the ratio of your anion that you get from your salt to your weak acid concentrations are the same number. You'll see in that case, if this equals 1, if those two concentrations are the same number or pretty darn close to the same number, that log will be 0, and you would end up with a situation where the pH is equal to the pKa.